go. Right, I already said that. So now we're going to be referencing this guy, right? This is the biggest of the 3 handouts that I gave you. And I'll try to note in the slides, I think I got them all added in there this morning. So if you have the slides printed out, if they don't have what page to reference in here, but I just added that today. So if you wanted to write that down on your slide printouts, you can. I'll point them out as we go. First, we're just going to start with some general concepts, right? So with seismic design, the general goal is to make sure that the structure will survive a major earthquake, but we understand that there could be severe damage that is sustained, right? And the level to which we design, or the level of the condition, I should say, that we aim our structure to be in after an earthquake depends on a lot of factors. One is definitely the use of the building, right? So we would definitely want a hospital to be functional after a major earthquake, whereas, like a shopping mall, maybe that's going to be significantly damaged and unoccupiable, right? So the use of the building plays a big role in all of our load designations, but especially with earthquakes. So when we are figuring out the loads that we're going to use to design beams and columns and floors and diaphragms and walls, we have to think about how to relate these static forces to the actual event, right? So there are a number of different ways to analyze and design for seismic loads. The most common one uses a static approach, and that's what I'm going to be teaching in this class, right? So we simplify the actual event, what's really happening, which is a dynamic phenomena, right, into what we call equivalent static loads. So the actual response is generated by the mass of the building trying to catch up to the motion at the base, right? So the ground is accelerating the base of the building. The rest of the building that's above the ground, we consider it to be lumped masses at each floor. And then that's force equals mass times acceleration, right? So this is where structural dynamics is a topic that you could take in graduate school. If you're interested in structures, I highly recommend it. That's probably my favorite class, one of my favorite classes of all time. And you'll get to really dive into that side of things. We're going to get a little bit of an intro, a little bit of a taste of it in this class. But we're only in the context of how do we relate that to our static analysis, right? So we're not actually going to do any dynamic analyses in this class, I promise. Everything is static, but we got to talk about it for the background purposes. All right, so we take those inertial forces, right, F equals ma at every floor, and we try to figure out what equivalent static loads could be applied that would generate the same displaced shape of the building as the actual earthquake. So that's the goal. All right, so some factors that affect seismic design forces, right? First, the size of the earthquake is a big one, right? And there are a lot of different ways to quantify that. We have the Richter scale. There's the other one, I think Mercalli or Mercalli or whatever it is, right? There's a lot of different ways to quantify the size of an earthquake. The one that's most useful for us would be the peak ground acceleration, or some kind of representation of acceleration, right? Because we want to map it back to F equals ma and get forces out of it. So we use the peak ground acceleration to represent the size of the earthquake that we're designing for. And then we need to know the mass of the structure at each floor above the ground. That one's pretty straightforward to figure out. We also need to know the natural frequency of the structure. This is the function, this is a characteristic that is a function of mass and stiffness. So we call that a dynamic quality of the structure. Mass, again, is pretty easy to figure out. Stiffness, as you are learning, right, with the finite element method, You know how to get that stiffness information. In practice for seismic design, it depends on the structure, but if we have a finite element model, we can usually obtain the stiffness straight from that finite element model. If we don't, or if we're using a simplified approach, there are some ways that we can estimate the stiffness for certain design assumptions and purposes. So, but one way or another, we get some representation of the stiffness and the mass to figure out the natural frequency of the structure. And then the lateral force resisting system plays a big role in determining the magnitude of design forces from earthquakes. So this is where we're going to be seeing more talk about braced frames, moment frames, shear walls, and not just which category are they in, is your LFRS in, right? Those are the three main categories, but what type of shear wall, what type of braced frame, what type of moment frame is it, what material is it made out of? All of those things will have a big role in the magnitude of those forces. So we'll talk about that this week as well. And then finally, the risk category, which is directly tied to the use of the building. So I'll define what those risk categories are shortly. And then another note, right, you're probably all familiar with this concept. Natural frequency is the inverse of the natural period of the structure. So the period is how long it takes to complete one cycle of oscillation, and the natural frequency is how many cycles of oscillation occur in 1 second. And that is, I like to think of it as the way the building wants to move when it's swaying back and forth, right? That's how it wants to move, the rate at which it oscillates. All right, so we need to figure out the design earthquake, which is represented by these parameters, SDS and SD1. The full phrase for it is a mouthful: design spectral response acceleration parameters. So graphically, it's represented by this design spectrum, right, where the maximum has kind of a plateau defined by this one parameter, SDS, and then a point here corresponds to 1 period, or to 1 second period, and that is defined by SD1. So we come up with these two values to generate a design earthquake that has a spectral graph that looks like this. And you may or may not be familiar with spectral graphs. If you're not, don't worry about it. It's not something that you need to know for this class. This is just background purposes for the most part, but to understand what this represents, right, we're plotting essentially a magnitude of response, in this case acceleration, with the natural period in seconds. Sometimes we also use we use frequency instead of period on the horizontal axis. That's more, we see that more with wind analyses than seismic analyses. In seismic, it's always natural period on the horizontal axis for spectrum. And let's see. So just kind of a background there, right? So, and then to give you an idea, right, I think some context helps too. So the natural period of the building, as the building is taller, the natural period will be longer, right? So tall buildings would kind of fall over on this side of the spectrum, whereas shorter buildings would fall more here. So that's one reason that shorter buildings are more susceptible to sustain earthquake damage. Tall buildings can ride it out a little bit more easily. They're more flexible, and they actually perform pretty well in earthquakes if they're designed properly, right? But shorter buildings are the most at-risk structures, especially unreinforced masonry buildings, which is another topic, an entire other class, and so on. All right, so in order to determine this design earthquake, we need to figure out these 3 items: the size of the earthquake, right, the natural period of the structure, and then the local site coefficient. So that's tied to the type of soil at the location of the building. And I'll talk more about that in a moment. After we figure out those pieces of information, we can calculate these SDS and SD1 values. And then once we do that, we need to find the seismic design category, which is a hazard classification. That's going to be based on the design earthquake and also on the risk category of the structure. So we'll talk you through both of these processes. First, we'll look at defining the design earthquake. All right, so the two items noted on this slide are the baseline parameters, which are found on maps. This is SS and S1. SS refers to the short period response. S1 is the 1 second period response. And these are based on location, thus being mapped. I'll show you those maps in a moment. After we obtain those values, we need to find the local site coefficients, FA and FV. Those are based on the type of soil at the site, and I'll point that out in a moment as well. All right, so first, the maps, and this is where your handout comes into play. So this is on, this first one is on page 5 to 6 of your handout. And there are separate maps for Alaska and Hawaii, but we'll just look at the continental US map here. So this one is specifically for SS, the one parameter of the two that we need to find that are mapped. And as you can see, there are a lot of closely spaced contours, right? So, did they print funny or are they?
Well, I was just sad Alaska's not on here.
Oh yeah, oh, yeah, I know. Alaska has like 5 or 6 different pages in the maps. But yeah. So we used to, back in the day, actually use these maps to obtain these values. So you can imagine, you know, how accurate that was, because if you're looking at these numbers, especially in, you know, a place like California where there are just some closely spaced contours, it can be really hard to pinpoint what your actual value is. And these values are listed as a percent of gravity. So if you see 11 on the map, that means 0.11 times G. In our calculations, we would not substitute anything for G. We would just use 0.11 for SS. S1, all right, if you flip the page, a very similar map, right, with some slightly less densely spaced contours. This is for S1, all right? And if you read the notes at the bottom of these maps, you will see that ASCE 7 tells you don't use these maps, right? Everything is online now. All the data is online. There's an online tool that I will show you that you will use in this class and that you will use if you go on to work as a structural engineer. So we'll get to that in a moment. But the reason that I provided these maps in your handout, right, is because I think it's nice to see the big picture. It's helpful to get a feel for where the hot spots are across the country, if you will. And then also just for perspective, right? Like this is how it used to be done. Kind of nice that we don't have to read those maps anymore. And then, you know, so obviously you can see high seismic activity on the West Coast, no surprise there. Here in Bozeman, we're in a very high seismic zone thanks to Yellowstone. And a lot of the country is very low seismic, but there are a few locations where they're at greater risk. For example, where are my Midwest people? Who knows what this guy is right here in the middle? Southern tip of Illinois, extending down along the border of Kentucky, Tennessee, Missouri, and Arkansas. Any guesses? All right, that's the New Madrid Fault. Have you heard of the New Madrid Fault? I see a few yeses, a few nos. Okay. So when I was in graduate school up here in northern Indiana, there was a magnitude maybe 4, it wasn't very big, maybe a magnitude 4 earthquake with an epicenter in southern Illinois. And I felt it. It woke me up in northern Indiana, all right? The New Madrid Fault is notorious for having earthquakes that are felt far and wide. And here's a map that kind of demonstrates that, right, visually. So this is comparing a magnitude 6 earthquake on the New Madrid Fault to magnitude 6.7 in Southern California. And how far that shaking was felt, what is the area of damage, and so on. So this is all going back to the type of soil at the site, right? In California, it's all bedrock and hard rock there, right? So the earthquakes, they don't travel very far. They dissipate pretty quickly. Over in the Midwest, there's a lot of soft clay soil. And so when the ground shakes, those waves just go on and on and on. Now this is from 1895. Earlier in that century, in 1811, 1812, there were a series of earthquakes, and the biggest ones were like magnitude 7 something. And those were famous for being felt as far away as Canada. They say the church bells rang in Boston, and the earthquake actually temporarily reversed the flow of the Mississippi River. So a lot of weird things happened, and you know, back in the early 1800s, you know, people were just kind of like, whoa, what is going on? You know, the earth is, you know, the world is ending. I think there were also reports of like lights flashing out of the ground, and that was most likely due to quartz crystals being activated and you know, releasing some of their piezoelectric activity. I don't know, but anyway, a lot of weird things went on during that earthquake, and there are a lot of interesting accounts related to it. But just for perspective purposes, right? The type of soil at the site makes a huge difference. All right, so that brings me to table 20.3-1, which is on page 4 of your handout, so before the maps. This is where we determine the site classification, all right? So on the right-hand side of the table that I have put a big X over, you may recognize some of those terms. Anyone taking geotechnical or has taken geotechnical engineering? All right, so you know shear velocity. Have you heard of that yet in that class? No? Okay. Well, you may or may not. I don't know if they teach that anymore, but anyway, good news is you don't have to worry about that in this class because as a structural engineer, the geotechnical engineer will give you a report, right? The geotechnical consultant give you a geotechnical report, and that report will tell you which one of these categories your soil is in. So that's all you need to know, A, B, C, D, E, or F. In this class, I will take the same approach. I will describe, you know, maybe hard rock or soft clay soil or whatever it is. You just need to know where to go to look up which letter it corresponds to. If the site class is unknown, which is often the case early on in a project, the code says to assume site class D. So that's not uncommon, right? A lot of times we start calculating our loads before that geotechnical report has come in. And so it's pretty common to proceed with your calculations assuming site class is D, and then later on when that geotechnical report comes in, if it says, hey, it's actually C, you know, that's good news, because then you can go through and update your calculations and get some reduced seismic loads for your building. All right, so next up, right, once you determine that site class, and then you already have the SS and S1 values from the maps, then the next step is to determine these site coefficients, FA and FV. So those are from these two tables, which are also on page 4 of your handout. You enter them with the site class and then with the mapped value. If the mapped value is between one of these items that are in the table, right? So if you're between 0.5 and 0.75 for SS, for example, you still use this table, just interpolate linearly between the values, right? So if you were site class B, you wouldn't have to do anything because it's the same value across those columns. But if you were site class D, and you would have to use a value somewhere between 1.4 and 1.2 according to wherever you were between 0.5 and 0.75 on SS, right? So in the text excerpt, there's a little footnote that explains linear interpolation in case you need a refresher. So you can look to that if you need to. All right, once you figure out those FA and FB values, then you can calculate the design earthquake. So first, we calculate what we call the maximum considered earthquake. And this is a magnitude that we use for some advanced types of analyses that we won't cover in this class. In this class, we're going to use the design earthquake, which is just 2/3 of the maximum considered earthquake. And that's what's represented by this spectrum graph, right? All right, so now after determining the design earthquake, you can figure out the seismic design category. So we'll look at that now. Seismic design category is based on the design earthquake and also on the risk category. So these are found in two tables that are also on page 4 of your handout. We need to check both and use the worst case. Oh, I thought I had an image of those tables on there. I don't. Well, anyway, you can look at it if it's in front of you. All right, so you enter those tables with your design earthquake value, either SDS or SD1, depending on the table. And then you enter it with the risk category. So I got to explain risk category. That's why I don't have them yet. All right. Risk category. Risk category is, you can find some information on the first page of your handout, right? So that's the very first table in the environmental loads handout. This is something that applies to all environmental loads, not just earthquakes. I'm going to explain it a little bit more clearly than what's shown in your handout. So basically, we have 4 different risk categories. Risk category 1 would represent a very low hazard to human life in the event of failure. So that would be like agricultural facilities, storage areas, places where you wouldn't expect people to be spending a lot of time or very many people to be there. Risk category 2 is what most buildings fall under, right? And that is just defined as anything that's not 1, 3, or 4. Risk category 3 are those buildings that would pose a substantial risk to human life if it failed, or a significant economic impact or mass disruption of day-to-day life. So ASCE doesn't get too specific, it's kind of vague on this. It just says large number of occupants or high-density public assembly. The codes get more specific. So the IBC, the International Building Code, says 5,000 occupants or more, your risk category 3. If your building is going to have or could potentially have 300 people or more in one area, such as a ballroom in a hotel or a convention center, something like that, then your risk category 3. Another criteria is if the ability to exit is restricted or if people need help in exiting the building, so jails, nursing homes, elementary schools, daycare centers, things like that would be risk category 3. And then any utilities or power plants. And then the highest level of risk category are those essential facilities that we want to remain operational in the event of a major earthquake, such as hospitals, right, emergency shelters, emergency utilities or backup power, and then nuclear facilities. Right, that would be a major disaster if those were to fail. Remember Fukushima? They're still dealing with that fallout. So, yeah. All right. So then that brings us to seismic design category. Do I actually have? Oh, I do. Okay. I do have the tables on the slides. It's just coming up. All right. So, seismic design category, don't blame me, I didn't come up with this, but conveniently, it's the same letters as site class, but they are not correlated at all. So don't confuse the two, right? So seismic design category A through F. A, B, and C represent low to moderate hazard level. Anything D or higher is considered high seismic zone. So for perspective, right, eastern Montana, much of eastern Montana is a very low seismic risk or seismic hazard. Category B is low. That would be like Billings or Great Falls. Category C, moderate. That's Missoula. Bozeman, here we're in category D. And then E or F are both classified as high hazard level. These are defined as being very near a major active fault, such as Southern California. So what's the distinction? How do you tell whether it's E or F? That comes down to the risk category of the structure, right? So risk category 4 would be seismic design category F if you're in a high seismic hazard area, right? Very near a major active fault. So what is the point of seismic design category? It doesn't actually, it's not a numeric value that's attached to it, right? So it doesn't factor into, it's not something we plug into our calculations or anything like that. But it determines certain requirements or limitations that are imposed on our design. So for example, it dictates whether we can use certain methods of analysis, like the equivalent lateral force method that we are learning in this class, right? It tells us whether a certain structural system is allowed to be used, right? And it also tells us if there are any height restrictions on the building. All right. Questions so far? All right, so here we finally made it to those tables on page 4. All right, so this is where you would enter with risk category and SDS, or in table 2, risk category and SD1. Again, you have to check both and use whichever one gives you the worst case result, right? All right. So the next slide, this is an example of where seismic design category applies, right? So this is just FYI. You won't need to use this table at all in this class, right? Because this is the example of saying, right, there are some scenarios where the equivalent lateral force procedure is not permitted. That's what the NP stands for in the table. In this class, we are only using the equivalent lateral force procedure. So you don't have to worry about this table. It's just here for reference. The other methods that are showing up in the table are always permitted, right? So these are dynamic analyses, and they're more involved. They're also more accurate, which is why they're always permitted. But we generally don't use those methods unless we really need to. All right, so this is showing you the online tool. So you go to hazards.atcouncil.org to use this, and we can use it for wind and snow loads as well. I'm going to introduce it in the context of seismic loads, of course. So I Googled, or not Googled, but you can search by address or enter exact coordinates. And just putting in Roberts Hall, right, it pinpointed the location of Roberts Hall here. So you have to choose the reference document, the risk category, and the site class in order to get any information, right? In this class, you will use this to get those mapped values SS and S1. It will also spit out everything between that and SDS and SD1. So you can use that information to check your work, but you have to go through the process and show the hand calcs and the table values that you use to get there, right? So, for example, we will choose ASCE 716 as the reference document. Make sure that you pick the right one because it will change the values if you pick a different one. Risk category, right? We have to enter that just to get the results. site class, same thing. So those lower two items, they actually have nothing to do with the mapped values, right? They're independent. But we still need to input it into the program because the program calculates a lot of other things for us. All right, so it will give you then basic parameters, right? Those are the first two is what you're going to be after, the mapped values. And then it'll calculate for you the maximum considered earthquake and the design earthquake. So again, you can use the rest of the output to check your work, but you have to go through that process yourself. So only use the, only purely report the SS and S1 values. So here's an example of Bozeman's city code criteria, right? So again, you always want to check local requirements. And in Bozeman, it says we are seismic design category D. So even if you happened to go through that process and say, oh, hey, this says I could use seismic design category C by the calculations, Bozeman says, nope, always use D, right? So you have to use D in Bozeman. Another example, all right, in Minnesota, there are no requirements for earthquake design. I think the city of Chicago is similar, or maybe they just recently added one. I don't remember. I'm gonna have to look at that. But so some states, right, if they're entirely in a low seismic area, they might not have any requirements for seismic design, which is kind of surprising, a little unnerving, because it's not like it's impossible for them to be, at risk to an earthquake. But as a structural engineer, we always, even in those situations, right, it's good practice to design your buildings to resist a minimum baseline lateral load. And I'll point that out to you when we get through the calculations. All right, how are we on time? A few minutes left. All right, so I think we'll get through at least the calculations of the equivalent lateral forces. All right, so once we figured out the design earthquake and seismic design category, the next step is to find the seismic base shear. So that's a really simple equation, right? Just V is equal to CS times W. W represents the total seismic weight of the structure, right? So that's basically summing up all those lumped masses that are above the base. It essentially is coming from dead loads above the base, and then sometimes we include live loads or a percentage of the snow loads. In this class, you don't have to worry about that. It will just be, what is the weight at each floor, sum those up, right? So we'll keep it simple. And then CS is what we call seismic response coefficient. So that is calculated by one of the design earthquake parameters, SDS, divided by a modification factor R, which I haven't defined yet, and then IE, which is the importance factor. So I'm going to define that as well. All right, so first up, R. R is based on the lateral force resisting system. So it basically accounts for how well the building will respond to a seismic event, right? So we need to figure out what R is for each orthogonal direction separately, because we might have a different lateral force resisting system in, right, two orthogonal directions, right? You could have shear walls in one direction and braced frames in another, and then that would give you two different R values for, one for each direction, right? We also might sometimes have more than one type of system in a given direction. So if you have a shear wall and then there's a braced frame right after it in line, you have to look up the R value for both systems, and then we choose the one that has the smaller value because that's more conservative. So this is a common mistake in this class. A lot of students will be tempted to add them together or find the average. Don't do that, just use the smallest one. So the example here, right, we've got, moment frame, shear wall in the X direction. So in that direction, we would use the R of 5, which is the smaller one. And then in the Y direction, we have braced frames. So the R and the Y would be 6. All right, so how do we find these R values? This is all in the wonderful 2.5 page table that starts on page 9 of your handout. So it's organized by category, where category A is your bearing wall systems, B is building frame, C is moment resisting frames. There are more categories beyond that, but we're not going to worry about them in this class, all right? So we're just going to worry about the first 2 pages of this table. You can ignore the 3rd page. And we're also going to be able to ignore a lot of the columns in here, all right? So you can cross out these guys. We're only going to need that first column, which gives the lateral force resisting system, and then this column that gives us R. And then over on the right side, we have height limits and other restrictions that are dictated by the size we don't care about in this class. So the first category is category A, bearing wall systems. Under this category, you will see a bunch of different types of shear walls. And the response modification coefficient, R, is the main thing that we're interested in using this table. So you'll see a range of values from 1.5 all the way to 5. I don't know if there are any higher than 5 in category A. That might be the highest one. Maybe there's a 6. I don't remember off the top of my head. But basically, right, this list continues, and the distinction, right, between bearing wall systems and the next category, which is building frame systems, is that the bearing wall systems are also responsible for supporting significant gravity. So those shear walls not only are necessary to resist the large seismic loads, but they also have to support a lot of the vertical loads of the building. If you have a shear wall that is in a building frame system, right, because you'll see the same list of shear walls in category B that you saw in category A, that means that those shear walls are not responsible for supporting gravity loads, or not significant gravity loads anyway. So if those shear walls fail, it's less critical because there's a separate frame in place that can hold up the vertical loads of the building, right? So it's still vertically supported in that situation. So in category B, you will see shear walls as well as braced frames, right? So braced frames are never responsible for supporting significant gravity, so you won't find them in the bearing wall category. All right, I gotta go back to this slide because this is where these items are pointed out. So on the right side, right, this is where seismic design category comes into play. And you will see B through F, right? Category A is not even included on this table because that is the lowest seismic hazard category. So if you're in category A, there are almost no restrictions at all. Like you basically just design your structure to resist 1% of the building weight and call it good. But if you're category B or worse, then you have to go through this process and check all of these things, right? So for a given system and a given seismic design category, you can look here to see if there's no limit on your structure, which is the NL, or if there's a height limit, right? So a number represents the maximum height in feet, or maybe that system is not permitted in that seismic design category and you have to choose a different structural system. So that's what the NP stands for. All right, so bearing wall systems, building frame systems. Next is moment resisting frames. So that's in category C. That'll be on the second page of this table. And moment resisting frames may or may not support significant gravity. Sometimes they do, sometimes they don't. But regardless, they're all lumped together in this one category, moment resisting frame systems. And you know, everything else is the same. So you'll see And in all of these categories, right, you look down the list, you'll see different materials listed. You see steel, you see reinforced concrete, masonry. In the shear wall category, it doesn't show up in my slides, but in your handout you even can see, wood, right, plywood or gypsum board. There are a lot of different materials that show up in shear walls. So just FYI, right, a lot of different things. And we're not going to get, in this class, we're not going to worry about what the difference is between all these different types, right? So I'll just tell you for perspective purposes, but you don't need to remember this. The special, right, so in all of these systems, there's special shear walls, special brace frames, special moment frames, or ordinary or intermediate. So basically what that means is that the special ones are designed to be extra ductile. So the connections are designed in a certain way. They have extra requirements on how they are detailed, and they have better performance in earthquakes. So those structures or those systems have higher R values because that allows you to reduce the seismic loads on the structure because they are designed with such significant requirements and restrictions. And then similarly, right, along those same lines, if you compare the same shear wall systems in category A to category B, you'll notice that in category B, where those shear walls are not responsible for supporting that extra gravity, those R values are higher generally. They're never lower, right? I think there may be a few cases where they're the same, but I'm pretty sure in every case they're higher than they are in category A. And it's the same reason, right? If it doesn't have that extra responsibility, then we can design it to, I guess, a lower standard, if you will, right? So the ones that have to support the gravity are designed to a higher standard. All right, let's see, skipped. Oh, no, okay, that is the right direction. Right, okay, so that takes care of the R factor in this equation. Next, we need to talk about this IE. This is the importance factor specifically for seismic loads. So importance factor is another one of those things that shows up for different environmental loads. This can be found in the first page of the ASCE handout. So this is the table at the bottom of that page, 1.5-2. And for seismic loads, right, you'll find that IE on the far right. It's based on risk category. So you can see for these risk category 4 structures, it's a 1.5 seismic importance factor, right? So we increase those seismic loads by 50% for those structures compared to an ordinary building. All right, there are some limits that we need to check on this seismic response coefficient. So 2 equations to consider. One has this 0.044 SDSIE as a lower limit, right? And the other one has 0.01 as the lower limit. So that means no matter what you calculate as the lower limit using this equation, you cannot design it for less than 1% of the weight of the building, right? And that's why in places like Minnesota or Chicago, maybe not anymore Chicago, but it used to be Chicago, where there are no seismic requirements, any engineer who knows what they're doing or is, actually paying attention would design it to be able to resist at least 1% of the weight of the building applied laterally. This upper limit on CS is technically optional, but it's beneficial. So we definitely want to check it and make sure that we don't go over, right, the value that we need to. All right, so in this upper limit calculation, we see another item. This is T, which is the fundamental period of the structure in seconds. This is, we already talked about it, right? It's a function of mass and stiffness. We can get it directly from the finite element model, but the equivalent lateral force procedure allows us to use an approximate natural period instead of the exact one estimated by the model. And we do that by using this equation CT times HN raised to the exponent x, where HN is the height of the structure in feet, and the other two values we get from this table 12.8-2, which is on page 12 of your handout. So this is based on the type of the structure that you have, and there's only 4 categories really, right? So you have the moment resisting frame, and then subcategories, steel versus concrete, or you have steel eccentrically braced frames, steel buckling restrained braced frames, and then all other structural systems. So most buildings will fall into that last category, all other structural systems. One thing to point out, if you have moment resisting frame system, you only want to use this if that moment frame is the only system in a given direction. All right, so that comes from all the stuff that's written in that table under moment resisting frames, right? Because this assumes that the frames resist 100% of the required seismic design force. So just use it if that's the only system in a given direction. Otherwise, you can't really say that those frames are designed to resist 100% of the required force, right? Unless you're the engineer and you design it that way, but in this class, we're not gonna go that far. So, all right. Right, and then just a reminder that metric units are provided in parentheses. So you can ignore the parentheses value for this class. All right, so that gets us to the base shear calculation, right? After we've gone through that CSW and then checked the limits on CS. Now the next task is to figure out what percentage of that base shear gets applied to each level of the building. And this is where this equation comes in. So Fx represents the force applied to level X above the base, and we have to calculate another factor called CVx, and we use that to multiply it by the base shear to figure out for each level. So that's essentially a weighted average, if you can kind of think of it that way. So it's going to be the product of the weight of the individual floor that you're considering times the height from the base to that level raised to an exponent k. So that product in the numerator, and then the denominator is the summation of that product for every level above the base. All right, so k, that exponent is based on the natural period of the structure. If your natural period is 0.5 seconds or less, you just use k equals 1, so that's a linear variation with height. If t is greater than or equal to 2.5 seconds, you use k of 2. And if you're in between 0.5 and 2.5, then you interpolate linearly. So in this class, we'll just probably be dealing with k of 1, so try to keep it simple. All right, so visually, this is kind of what it ends up looking like, right? These are your equivalent lateral forces. If you add them up, it should equal the base shear, right? That's what we're doing. CVx represents a percentage of the base shear applied at each level. Any questions so far? All right. Oh, all right, we're almost done with this part anyway. All right, so this is provided in the text handout, right? So this is towards the end of the seismic loads chapter. And it basically just outlines the steps for this whole process, right? Separated into 2 parts. First part, finding the SDC and the design earthquake. Second part, determining the seismic forces. It also references the tables that you'll need in ASCE 7, so this can be a useful thing to guide you as you go through it. Also, if you might be something that you want to hang on to in the future if you decide that you want to stick with structures, because this could be useful in the office as well. All right, another thing, the last thing I wanted to point out, right? the order that these things are presented in is appropriate, but not necessarily fixed. So there are some items that you could do before or after others. Not everything can be mixed up or thrown around, but a few things, right?